A hot air balloon is 8.74 meters in radius. Assume it is spherical, which it's not, right? Contains hot air with a mean density of 0.9486. Calculate the lifting capacity of the hot air if it is surrounded by air with a density of 1.34, right? So it's maybe a little more dense. It's cold out or something like that, right? Okay, so here is this balloon. A balloon. And it's in air. And maybe we've tied it to the ground, right? So it's going to exert a force upward, right? There's going to be a force upward of the buoyant force. But there's also going to be a downward force. This air, the hot air even weighs something, right? It's lighter than air, but it's not zero mass, right? So there will be a downward force at the weight. And the difference between the buoyant force and the weight will be our lifting force, right? Okay, so let's figure out B first, right? So B is density of the fluid, which is the stuff around this right there. Okay, times the volume of the fluid displaced times G, right? So the density is this, right? Our buoyant force is going to be caused by the air, the cold air displaced, right? So 1.34 kilograms per cubic meter, right? Times the volume, which is 4/3 pi times 8.74 to the third times 9.81. All right, so 1.34 times 4 divided by 3 times pi times 8.74 raised to the third times 9.81. That's a lot of lifting force. That is, so 36,761.79 newtons. That's this force, right? So this is 36.7 kilonewtons, right? Roughly, right? Okay, that's just kilonewtons, or 36.8 kilonewtons, right? And then the weight of this thing, the weight is going to be mg, which is going to be the density of the hot air, right? I'll just say H, right, times the volume of the hot air times G, right? So the density of the hot air is 0.9486. The volume is the same as this, right? 4/3 pi times 8.74 to the third times 9.81, right? Okay, so I'm literally going to do the same exact calculation, only I'm just changing what the density I use, right? There's a shortcut here. I'll talk about it in a sec. All right, so insert 0.9486. So the downward force, this weight, is 26,024.059 newtons. Right, so we've got 26.0 kilonewtons down, right? So if we want to add some other force here, right? Some force plus 36,761.79 minus 26,024.059. That has to add to 0, right? If we've tied this thing down with this, whatever that force is, it's not accelerating, right? Okay, so it's the difference between these two. So I'm going to go this guy minus this guy. And I get that the net downward force that we'd have to exert is 10,737.7 newtons, right? Okay, which would be about 10,740 newtons. So the downward force we'd have to exert to hold it on there is its lifting force, okay? Now, this is a perfect one for using a shortcut, so I'm going to show you the shortcut here, okay? The shortcut is this, right? That the lifting force, right, is the buoyant force minus the weight, right? The buoyant force is rho of the fluid, volume of the fluid, times G, the weight. Oops. The weight is the density of the object times the volume of the fluid displaced times G. Well, the volume of the fluid is the same, right? So we can just simply go 1.34 minus 0.9486 times the volume of the fluid and the volume of the object are the same, right? This is so 4/3 pi times 8.74 to the third times g, right? So I'm just going to do this 1.34 minus 0.9486 end parentheses times 4 divided by 3 times pi times 8.74 raised to the third times 9.81. Bingo, we got the answer, right? It was 10,737.7 newtons is the net force, right? Density minus density. It's just super easy when you have to figure out the volume anyway.